It's about 25 years since frequency combs were first introduced, or at least kind of as we know them today. Their roots go back maybe 2 decades before that. So it's a kind of 25th anniversary. And then, yeah, just yesterday was the 20th anniversary of the Nobel Prize in Physics on December 10th, when Ted Hench and Jan Hall and Roy Glauber got the Nobel Prize. I think the kind of official poster was the two sides of light, kind of like Janus, the god. There was the quantum side with Roy Glauber and this very applied wave side that Hench and Hall were involved in. So anyway, yeah, history is kind of interesting. I think it's like how science evolves, how ideas evolve are always interesting too. So maybe I'll touch a little on that. So yeah, 25 years. These were kind of some of the first papers that I was involved in, and then also kind of simultaneously the group of Ted Hench. And I would say the history was like, the history is quite interesting in that I think Hench really had the ideas, and but in Boulder, we were fast. And we had access to some tools that they didn't. And so we could rapidly catch up and introduce, I think, the first like self-reference frequency combs. This guy I worked with, John Hall, he was really a phenomenal person, very down-to-earth scientist. And in fact, myself and this other postdoc, David Jones, you see Jun Yi was now, a world-leading scientist. He was a student with Jan Hall. He had left and had gone to Caltech. I moved into the lab. June came back. He was just back for a few months and was already involved in the projects that we were working on. But we did these kind of works, these 2 papers. And I remember we wrote the paper, we wrote the draft, we gave it to Jan, and Jan said, I need to call Professor Hench. And he said, I want to invite Professor Hench to be a co-author on our paper. And he said, because I want to recognize the fundamental ideas. And so Jan was always very collaborative and someone who, as intense as he could be and as focused in the lab, always recognized that it was more important to be a good friend, a good scientist. And so I think that was why Holtzworth, Udom, and Hench were added to this paper here. And of course, in parallel, they were doing a lot of their own work. And as I'll tell you in a minute, like why we could move quickly was related to some of the nonlinear optics pieces that were involved in making the frequency combs. So yeah, I presented this slide before. I don't think I will dwell on it, but like I've thought a lot about why this technology is important. And I think that slide really captures it, in that you have this coherent connection between microwave, electronics, and optics. And the frequency comb really unites the electromagnetic spectrum in a coherent sense. And it opens up new opportunities, as I already presented a few days ago. So I won't go into that again, but I just want to remind you of that. And if you care to look at that paper and think about it a little bit, maybe you will come to appreciate that more, and also maybe come to add some of your own ideas to that kind of a plot. I think that's really what's exciting about optical frequency combs. I also had shown this picture. I just want to re-emphasize it again, because honestly, like it's internally how I understand what happens. And I'll elaborate a little more on this. I had already mentioned that the frequency comb is a coherent connection. And by coherent, what I mean is that we can keep track of optical cycles in terms of microwave frequencies, which we can access. There's no electronics that go fast enough to count those cycles of light. Your eyeball, the fastest detectors we have, maybe they go to kind of picosecond, but you're still missing about a factor of 1,000. And so finally, this tool came along, the comb, that allowed us to keep track of those cycles. And in this picture, I like to think of these little wheels, each gear as being a cycle. And so as that gear rotates, the frequency comb, which is kind of this center reduction or multiplication gear, can keep track of each cycle. And I'll explain to you a little bit later. This very simple equation, it's perfect. We haven't found that it breaks, at least on average, on long terms. And I was a postdoc in the lab, and we made the first frequency comb, and Jan Hall, he looked over my shoulder and he goes, "That's going to break." He goes, "It's not going to work. It has to break somewhere." And I was like, "Whoa, what does that mean?" And I kind of took me a while to digest it, and I internalized it. And so actually for about the first 4 or 5 years of my career at NIST, I tried to figure out if there was a crack in this equation. And as best as we could find out, and then other people even added more digits, we didn't find that there was a crack in this equation. If you look short term, if you look very fast, there can be noise. But on average, this very simple equation holds. And what that means is that we can know the exact gearing ratio. And we don't want to push the mechanical picture too hard, but I like it. So I'm going to just tell you a little bit about that. But we can really understand this in terms of perfect ratios of teeth in these gears that I drew here. And as I explained the other day, is this comb, it's like if you think of any oscillator, a flywheel, if you had a windmill or some oscillator that's just going all on its own, when it's operating, it can do all of these functions. It can coherently connect, the microwave to the optical. It can do it in reverse, the optical to the microwave, and it can connect across the optical domain. And it isn't until we engage it, we have to enmesh some oscillator with the microwave side, or we have to connect to the optical side, that we can actually use it in this dividing or multiplying or translational mode of operation. So it's really surprisingly magical in that way, I would say. We'll come back to that in a minute. So why did people do that, and what existed before that? It actually, if you go back since the beginning of the laser, and particularly the continuous wave laser that Ali Javan developed, Ted Mayman made the first kind of Q-switch laser, but it was really a continuous wave laser, a true kind of continuous oscillator that Ali Javan made, a helium neon laser. And very early then, even people like Ali Javan said, "Oh, this could be a really good tool for measurement." We've taken time, and we've divided it up into these few femtosecond bins, a period of light. We can control it. And this could be a really spectacular tool for metrology. So as early as the 1960s, people were starting to think, well, if I'm going to measure something with light, but all the tools I have to measure are in the microwave domain, how am I going to do that? And you might say, well, we would use interference. And you all know examples of heterodyne interference from, tuning a piano or handbells. It's remarkable how it works. You can have two very high frequencies, ding, ding, and they sound almost exactly alike. But if you play them at the same time, you hear the slow wow, wow, wow beating between them, right? That can happen with light. So we could take two light waves and we could heterodyne them together. And these could be 500 terahertz each. And we could make 10 hertz or 100 hertz beat frequency that we could measure. But that would just tell us the difference of the frequencies. It wouldn't tell us how many cycles were in one of those frequencies. So people devised ideas on how could you actually get that absolute frequency. And it was this idea, one idea was a harmonic frequency chain. So if you take kind of a very fast oscillator, actually the definition of the second cesium clock, it's around 10 gigahertz. If you multiply that in factors of 2 to the 15 takes you from 10 gigahertz up to 300 terahertz. So you go a factor of 2, 20 gigahertz, 40 gigahertz, 80 gigahertz, 160 gigahertz, keep going up the chain. If you did that 15 multipliers, you would get to the optical domain, or 300 terahertz. Maybe I should have done one more. 2 to the 16 would have been like greenish light. You would get there. And people actually tried that. There were efforts in several labs around the world. This is an example from the Physikalische Technische Bundesanstalt, the PTB, where they built this frequency chain. These are like huge machines, right? And you could do it at one or two kind of labs. And In the bottom, it was easy, but especially in this kind of terahertz gap, which people still struggle with in optics, like how do you go from 500 gigahertz to 1 terahertz to 2 terahertz? It's really hard. They found clever ways to do that, and in this case, they came all the way up to 455 terahertz, a red color, calcium transition. So that was one way. Existed in a few places. And you can see here the date here, 1996. This was the first phase coherent connection from the microwave domain to the optical domain. It was built by the German team at the PTB. Professor Hensch, really smart guy. I told a story to some of you that the other day, but when I was a postdoc, I went to Gilla. I was actually, my training was in ultrafast lasers, and I was working in like a lab that was making high intensity laser pulses and doing nonlinear optics with them. And I read a paper that had Hensch's name. It also had another Nobel laureate, Ferenc Krauss, on it. 1996 Optics Letters, Nobel laureates published in Optics Letters in those days. And I took it to Jan Hall, and I said, hey, what do you know of this? Because it talked about carrier envelope phase. And he goes, I don't know anything about that. He goes, but that guy, you should pay attention to what he says. And it was Hensch he was pointing at. And he said, he has good ideas. He has good taste in science. And I thought, I didn't know what that meant. Took me several more years before I kind of understood what that meant. But Hensch he flipped the problem the other way. And he said, let's build an interval divider. Let's take a laser at F and 2F. I can easily do that with a nonlinear crystal. Can take a frequency F, I can double it to 2F, 300 terahertz to 600 terahertz. Can I put another laser exactly in between? And he called this an optical interval divider. And you can do that because if you take F and 2F and sum them together in a nonlinear crystal, and then you take the second harmonic of the laser in between, they come to exactly the same frequency. And you can use that to servo back to this laser and put it right in between. So now your gap went from 300 terahertz in half. And Hensch's vision was, well, we're going to build a bunch of those. It turns out it's still the same number, roughly speaking, 15 of them. And you start dividing down until you get to a place where you could actually measure the heterodyne beat between two of these interval dividers. He was inspired by this idea actually from the hydrogen atom, because it turns out that the energy levels in hydrogen have this kind of interesting ratio, just like this frequency division. And so his lifelong passion was hydrogen. It was 2s, 4s, there were these levels in hydrogen that corresponded to these division factors. It was quite insightful. It actually turned out this was a situation where the frequency combs first started to get used, because they would get down to gaps that were maybe 1 terahertz, and you couldn't detect the beat between two lasers that were 1 terahertz, but you could talk to some Japanese colleagues, Motonobu Kurogi, and he knew how to make a comb. We called it the Kurogi comb that could split that gap in terms of 10 gigahertz or cover that gap. And so this was the type. If you went to Hensch's lab in the late 90s, he had this set up. His postdoc at that time, Thomas Udom, was running that. Ronald Holsworth, who's now the CEO of Menlo Systems, or CTO maybe, was a grad student in the lab, and they had built this thing. So the story goes is that one day they said, hey, maybe we can get rid of that electro-optic comb and let's try a mode-locked laser. They had a Ti-sapphire laser. Thomas Udom told me that in 1993, Hensch actually said, I want you to work on this idea when you started PhD, and they were too busy making this thing, and so they never started working on the mode-locked laser until later. They put the mode-locked laser in and they saw, oh, it can see beats. Jan Hall was visiting Munich at that time, went to the lab. He saw the beat, and he said, Udom showed me. He came back and he said, we got to work on this. And so we started working. And anyway, so it was kind of this interesting history of ideas that leads to kind of early days of where we are now.